Hi, Dr. Cortez.
Hey, Tyler.
I gotta tell you, I'm having a rough time.
I'm sorry to hear that.
But it's just, we're doing ionic compounds in solution, right?
Yep.
But I just don't understand how this is a compound, but when you put water in it, or when you put it in water, it ends up as a solution of ions. I just don't get how, it's the same thing, right? You're just putting it in water.
Right, and so in the solid, you still have ions, right? The ions are just packed together in a lattice, all next to each other. So like, we're sitting at this table, and we're next to each other, right? And there aren't other spots for us to be, right? There's no more chairs at the table, so we're kind of stuck here.
In our lattice.
In our lattice.
Okay.
Right? But when you add water, the ions now have a choice. They can be either in the lattice, or if they choose to, they don't really choose, but they can disperse and interact with the water molecules.
So you're saying that they don't magically become ions when you put them in water. They already are ions.
They already are ions. It's just that they're in the solid. They're in a lattice, locked in their places. And when you add water, they're freed from that lattice, and they can then move around in the solution. Okay. And so it's kind of like we could choose to move to other seats in this room. Right?
Okay, so right now we're saying that we're in a solid, right?
Right.
We're sitting next to each other. So if we were to magically get dumped into a solution of water,
yep,
just water, then we'd be able to move around and sit at different places.
Yep.
Okay, so that was an example of being in an aqueous solution?
Aqueous solution. Yep.
Right, so now that we're not in the lattice, I can sit over here and you can sit over there.
Right. And if there were, a class, we'd have other, ions sitting around at other tables, and maybe it's not a saturated solution, so there are empty spots. So welcome to the post-class recap on ionics, compounds in water. And one of the things I noticed students were having difficulty with was deciding what ions actually form when an ionic compound dissolves. And so the first step is always going to be identify what the ion's identities are. And so I have nickel acetate, that's that green compound. This is the formula for nickel acetate. And acetate is one of those polyatomic ions that we asked you to memorize, right? And so the name tells us what the ions are. The formula also tells us what the ions are. One of the ions, the cation, is nickel 2. And so I can write down its identity, nickel 2 plus.
And we knew that because it says 2 there.
It says 2 there. We could also know that by looking at the charges in the formula. But again, you have to know what this stands for. That's the formula for the acetate anion. And we know that the acetate anion has a -1 charge. Since there are 2 of them, that's -2 total. To balance that, the nickel has to be +2.
Okay.
Right? So we've identified the nickel ion. This is the acetate anion, and so I can write that down. So I've just written down the identities of the ions. The next thing is, how many of them are there? Well, in the formula there's only 1 nickel, so I just leave it as 1 nickel. So there are 2 of them, and so I write that there are 2 of them. What do you think of that?
I think that looks a little strange because you basically just wrote what this is here.
Well?
Don't you want to put the 2 on this side to tell us that there's 2 ions?
Oh, that's right, because when you write a subscript, that means that this is all bonded together. And when ionic compounds dissolve, the ions separate and they wander off in solution. They're on a kind of a random walkabout.
Right, so here, both of these ions are bonded to the nickel.
Yep,
right?
It's all one thing, all together. When you dissolve it, they all split apart, and so that 2 comes out in front. And if you could erase the parentheses,
sure.
We usually also don't put the parentheses on, but we put a 2. Right? So that's one nickel ion, two acetate ions. And notice I haven't broken apart the carbon and the hydrogen and the oxygens, right? That's a polyatomic ion that travels as a pack in reactions. Move on to the next one.
Sure.
Right? So, again, sodium phosphate, that's what was written on the bottle. Na3PO4, that's the formula. And so I write down the identities of the ions that are there. I know that sodium forms an Na plus 1 ion, right? Because it's in the first column of the periodic table. The PO4, that's one of the polyatomic ions I remember from my sheet. PO4 3 minus. So we've identified what the ions are, and now we just have to adjust for numbers.
Right, so there's 3 sodiums, so you would want to put a 3 there.
Out in front again, right? They're not 3 sodiums that are all linked together, which would be a subscript. They're 3 separate sodium ions, so the 3 is out in front.
Right, and although it might seem tempting to put a 4 down here because there's a 4 at the end of this oxygen, this phosphate is 1 ion, and it's going to stick together, right?
Yep.
Like a pack, is that what you're saying?
Like a pack.
Okay,
like a
so
pack.
we can't break up the phosphate wolf pack.
Nope.
So that means there's only 1 of these ions. If there was more, we'd have parentheses, and we'd have another subscript there.
Yep. Good. So now that we have the ions, we can actually start to talk about chemical reactions. Because when you do reactions of ionic compounds in solution, they dissolve, they break apart into their ions, then you mix the solutions, and it's the separate ions that actually react. And usually, not all the ions react. Some of them just hang out and watch. They're called spectator ions.
Right, like at a football game.
Come on, Tyler. Come on.
No, Dr. Godes, there's too much chemistry over there.
We can do this. We can do this together. Come on in.
Okay.
We'll go through it step by step. Right, so the other thing that we learned about today were molecular equations, complete ionic equations, and net ionic equations. Right, so different ways to write exactly the same thing, and they're used for different purposes. Right, so we have nickel acetate and sodium phosphate. And guess what? When I mix those two things together, they're going to react.
Okay.
Right, and so here I have some nickel acetate, nickel 2 acetate, and here I have some sodium phosphate. Right, and this is what I get when I go to the stockroom. This is what you actually take off of the shelf, right? Those bottles. Well, when you put them in aqueous solution, they dissolve.
Okay.
So you don't have solids anymore. And so up here, this is the molecular equation. And the molecular equation, basically, you write down the compounds that come off the shelf, right? You write the full formula for each one.
Okay. So if I were to read off the formulas from this, that's exactly what you put right here.
Yep.
And then this is what you put here.
Right. Nickel 2 acetate and sodium phosphate.
All right, less scary.
Right? But you recognize that, oh, we don't have the solids reacting, we actually have the solutions reacting, and so we say AQ.
Okay.
So if I react these two, so I'm going to add the sodium phosphate to the nickel solution. So a reaction happened. It's no longer a clear solution. We can't see through it. And that means that small particles of solid formed. So a solid formed. And that's one of the products of this reaction. Right? That's how we can tell that our reaction actually happened. It happens to be a light green solid, and so I know that that's actually a nickel product.
Okay.
Okay.
Sweet.
So our aqueous solutions reacted, and we formed a nickel product. And it turns out the other compounds, ions, stay in aqueous solutions, stay dissolved.
Right, which is why they say AQ.
AQ, and why this says S for solid.
Right, and solid is that that sort of milky looking opaque.
Yeah, if we let it settle long enough, it would settle out. But the particles are so small that they stay kind of suspended. It's like silty water.
Okay.
Right? Let it sit long enough, it'll settle out.
Okay.
Okay, so I've balanced this equation, and you can probably balance it pretty easily. But one of the things you'll notice, so I wrote these in color so that you could kind of see what's happening. So we have a cation and an anion in green, a cation and an anion in red. When these two react, what do we have? Well, we still have a green cation, but its partner is no longer the green anion. Its partner is
The phosphate.
the red anion. Right? It just switched partners. If we look here, the sodium and the phosphate together, well, now the sodium is partnered up with the other anion. So it's basically just switched partners. It's called a metathesis, actually, or a double exchange reaction. So that's the molecular form. We write it as if they were all molecules. We put all the partners kind of together.
Okay.
But that's not really very honest, because we know that when we dissolve things in solution, the partners break apart. They dissociate, and they're swimming around by themselves.
Right. So this anything with an AQ wouldn't necessarily be around as this molecule. It's just indicating that they're in the solution. So they're actually going to be separated into their different ions, like we showed earlier.
Exactly. Exactly. And so the next equation is the complete ionic equation, and all we've done here is taken these molecular, quote-unquote, molecular formulas and split them up into their actual constituent ions, just like we did in the first part of the video. So the nickel acetate splits up into nickel and acetate. The sodium phosphate splits up into sodium and phosphate.
Okay.
Now, what did not split up when I went from the molecular equation down to the complete ionic equation?
Well, your ions stuck together, your little wolf pack ions.
Okay, so the polyatomic wolf pack ions stuck together, so the acetates all stuck together, and there were 2 in each formula. There were 3 formulas, so 3 times 2 is 6. That becomes the coefficient, or the coefficient out in front. Right? 2 times 3 becomes 6. 2 times 1 becomes 2. Okay? How about products? What's different about the products?
Well, what's different is that instead of having separate ions, your solid here is actually a molecule.
Yeah, because it forms a solid, they're stuck together. And so we have to tell the reader, or the viewer, you, that those things are stuck together. That's what actually forms the solid.
Right, and you have your spectated ions here, your sodium and your acetate, that didn't react with anything, and so they haven't changed from this side of the equation to this side.
Yeah, so that's exactly, this is maybe more complex than it needs to be because it's showing everything that's there.
Okay.
But we have 6 acetates here, we have exactly the same thing over there. And so if there are things identical on both sides, we can eliminate them. What else is identical?
Well, your 6 sodium ions.
Yeah, the 6 sodium ions. So those are also identical on both sides of the equation. And if we eliminate those, we get to the net ionic equation. Nickel and phosphate form nickel 2 phosphate. Right? And so what this does is it says this is actually what's happening in this chemical reaction. It's focusing just on the things that actually change.
Right. And when we talk about net in chemistry, that just means overall.
Yep.
Right?
Yep.
So the net ionic equation is overall what's actually happening.
Yep.
Okay.
Thanks for viewing. This takes a little bit of practice. It looked like a lot of people still needed to finish those activities, and there are also more in the textbook. It takes a little bit of time to go through these, but you should get faster and faster with the more practice that you take.
All right.
Thanks for viewing.